In this recording, I would like to present another type of scheduling problem, which is real-time scheduling. This real-time scheduling is more relevant to the embedded system, and in this real-time scheduling problem, each process, each task has its own deadline. The real-time scheduling is to solve all the deadline of the given processes not to miss the deadline. So let me talk about what is real-time scheduling in more detail. And the topic of real-time scheduling is covered in Chapter 6, Section 6 of the textbook. And as I said, the real-time scheduling is a fun problem. The reason is the correctness of the real-time scheduling not only depending on the logical result of computation, but also the timing of this result that differentiate real-time scheduling from any other scheduling that we studied so far. The real-time scheduling is one of the vital parts in the design implementation of the mission-critical embedded system. And there are various types of real-time systems, and one dominant classification. One is hard real-time and soft real-time. And in the hard real-time, when certain computation cannot be done in a given time, which is known as a deadline, those missing the deadline is treated as the entire system failure. That is the criticality of the timing. So in that case, this is known as hard real-time. Unlike the hard real-time, the soft real-time, and when failure to meet a certain deadline is considered neither application nor system failure. It's just considered as less good. And so what's a good example for the soft real-time system? How about a temperature control? Maybe AC control, or what about the light control? So when it just missed the deadline, you may see some kinds of like a flickering in the light control, but it doesn't endanger your life, right? So it is classified, in that case, certain embedded system like this as a soft real-time system. And another classification of real-time system can be the periodic. In other words, every given period, certain task must be computed, right? In that case, every interval of the period, certain value needs to be recomputed, and that value must be available within that period. That is periodic. Aperiodic, and this is when certain event occurs, then the completion of the task must be done within certain period. And for instance, what is aperiodic? When you put the anti-brake on your car system, then the car must be stopped in certain millisecond. And that types of like a hard deadline is classified as a periodic real-time system. There are a variety of the scheduling algorithm designed for the real-time CPU scheduling. And in this lecture, I only cover two dominant scheduling algorithm. One is earliest deadline first and rate monotonic scheduling, EDF and RMS. In real-time CPU scheduling, and typically the thread is referred as a task. And so this is kind of interchangeable in the real-time CPU scheduling. So you can say thread and task interchangeable. And this Gantt chart is represent the periodic real-time system. So what I meant by periodic means, and each task has some kinds of interval, which is named as a period. Okay, and this period is repeating, and this periodic task, their ending time for this interval happens within this period. In other words, and this is the ending time, and here the ending time, and there's a deadline. Deadline is the end of period. So this is deadline, and this is deadline, and this is deadline, and this is deadline. So this task A, and this task has some CPU burst. That means this is the time it takes to complete the given task. And this ending time, again, must be done prior to this deadline. And the T is a period, and U represent the C over T, known as a utilization. And so by the same way, the B has a different period, and it has a different burst, CPU burst, and then a different utilization. Anyway, can we order these threads or tasks so that all the deadlines of each task can be met? So we have many variety of the ordering techniques, such as A, B, A, B, A, B, or B, A, B, A, B, A. In other words, the problem is what? Can we come up with the scheduling algorithm such that the deadline for A and deadline for task B can simultaneously met? And that is the real-time scheduling problem in the periodic environment. Let's take a concrete example to showcase the real-time CPU scheduling in the periodic environment. So let's say we have two tasks or two threads, A and B. These threads need to be completed every period. It should at least produce one value computation. So in other words, and at the end of the thread A, and the value for A, task A, will be produced. And the problem for the periodic means every interval of this given period, at least one computation result for the task A needs to be produced. If you're looking at this third period, and there are two results will be computed, right? And it's okay. And the requirement is what? For a given interval, at least one computation of the task A need to produce the value. And by the way, so let's look at the chart, the table. A, the CPU burst, the required CPU time to compute the value for A is a 15 time unit. And this value must be produced the period of 30 time unit. Every 30 time unit, A need to produce the result, which require 15 CPU time unit. So CPU utilization is a 50%. So let's look at B. B has the tighter period, and the period needs to be repeated every 20 time unit. And in this period, and the B need to produce a result in that require 10 CPU time unit. Therefore, the CPU utilization is the 50%. The good news is if we sum up the CPU utilization, which does not exceed 100%, so if we cleverly assign the schedule of A and B for the CPU scheduling right, then there might be some potential solution to meet the deadline of A and B for each given period. So let's take one ordering, which is A, B, A, B, A, B. If we just simply naively try this one, as you can see, we can meet all the deadline for A given period for the A, which is 30 time unit. However, when we come to the scheduling for the B, and every instance of thread B is missed the deadline. So even though the CPU utilization, sum of CPU utilization does not exceed 100%, and it does not necessarily mean there is a solution. That is the nature of real-time scheduling, CPU scheduling problem. So how about try the different scheduling ordering, B, A, B, A, B, and something like that. So let's try. So this is let's represent the real-time, the deadline. This is the deadline for the task A. So every period, an A need to produce one computation result. And so let me use a different color. So this is the deadline for hard deadline, or maybe soft deadline for the B, right? So let's see that. And at the beginning, now the B meet the deadline, A meet the deadline, and B meet the deadline, and A meet the deadline, and B barely made the deadline, and A meet the deadline. Now, starting from the time unit 80, the B losing is missed the deadline. If this application turns out to be soft real time, then starting from the time unit 80, the customer may see some kinds of uneasiness or some hiccup from the system, right? And however, if the task that I'm running right now is for the hard real time, then at time unit 80, and this is the point of time the task B missed the deadline, and this result in the entire failure of the real-time system. If this is the case, then can we find another ordering? Can we find another adaptive scheduling algorithm? And that is the challenges made from the real-time CPU scheduling problem. That means whoever scheduled better turns out to be the winner of the dominant market in the embedded system. So this solution is real and this challenge is real. And let's start from the earliest deadline first algorithm. So this is the way the scheduling progress. The scheduled thread or task with earliest deadline, and if earlier deadline thread appears, then preempt. And one of the beauty of this algorithm is works for periodic, aperiodic threads. It doesn't matter. And so let's take a look how this algorithm works. Okay. So let's say at the time 0, C arrives, right? So the C has the periodic task, which is interval like this. So this is the deadline for C, and this is a deadline for B, and this is a deadline for A, right? So since C is arrived at time unit 0, and it has earliest deadline, therefore C execute first. And then after that, and B arrived, and B still, its deadline is farther than C, and so it can execute B. This is 2. Then A arrives, right, at time unit 20. And so this is the earliest deadline, so A execute. Then C arrives at time unit 50. And since this is the earliest deadline, so this will execute. And B arrives next. And since B has the earliest deadline at that moment, so B will execute. And C arrives. So this is the earliest deadline, so C execute. And A arrives, so it has the earliest deadline, and so A execute. And then B arrives, and C arrives, and so on. Okay? So this, if you're looking at the way this algorithm works, and you notice this one, and this algorithm achieves 100% utilization. And this 100% utilization is based on ignoring the overhead, context switching overhead. And the downside is it is expensive. It requires the ordering by deadline. That means, and whenever the new task, new thread arrives, then system need to sort. In addition to that context switching, and system need to sorting all the tasks based on their deadline. And that means, think about it, every time the new task arrives, then sort, even though we know the best sorting algorithm is O, order of n log n. However, this is not linear, and this is not constant. Therefore, and one of the downside of earliest deadline first is it's too expensive to recompute the earliest deadline task. And also context switching, the frequent context switching due to the preemption cannot be treated lightly. And that's the downside of earliest deadline first algorithm. And you can do this at home. And let's say the task A, the CPU burst is a 30 time unit. The period for the task A is a 60 time unit. Therefore, the CPU utilization is 50%. And if you do the same thing for the B and C and sum up the CPU utilization, it sums up to 100%. That means this earliest deadline first algorithm can achieve the 100% CPU utilization in the real-time scheduling. the downside or the problem of EDF is, so far we assume the context switch is free. But it is not free, and it's actually costly. And the other one is, whenever the new task or new thread arrive, and what we need to do. And the system, the scheduling system, need to sort all the tasks in the system based on their deadline, which require n log n time complexity, which is not likely. Because of these two reasons, an earliest deadline first algorithm is really difficult to place in the real-time scheduling algorithm. So next algorithm is rate monotonic scheduling, RMS. And this RMS is quite well known in real-time scheduling research. And without knowing the RMS, and you will not be treated as the person who knows real-time scheduling. And so let me explain how the RMS is working. And this RMS only works for the periodic threads. And so if you're dealing with the scheduling for the aperiodic task, and the RMS won't work. So this RMS and each thread or task, they assign the priority. And those priority will be calculated based on the rate. So let me show you how that calculate the rate. So where it is? Okay. Here it is. No, I'm sorry. Let me see that. Oh, here it is. Okay. So let's say the table for thread A, B, C. The CPU burst is a 20 time unit, 10 time unit, 5 time unit. The period, the cyclic period is 60 time unit, 40 time unit, 30 time unit. The way to compute the rate is the inverse of this period. That means for A, this is a 0.0172533. Therefore, C has the highest rate, so we assign the C has the highest priority. And remember, once this rate is computed, and this is a fix, it won't change over the time. All right. So C has the highest priority, B has the medium priority, A has the lowest priority for this particular example. So let's go back how the scheduling works. So at the start of the period, select highest priority, right? And so in this case, C will be selected, and preempt if necessary. And when the CPU burst is done, then wait until the next period. In other words, and it just wait until the next period comes, right? So let's look at it. So C runs first, and then B comes in, so B runs next, then A runs, right? Now, the period for the C is done, therefore you need to start the C again. Now, we have A is currently running, C is just about to run. Since C has higher priority than A, therefore C preempt A. And after the completion of the C done, then A resume execution. At that point, A is the only task to be runnable. And B arrives, so B complete. And then C start, and A start next. However, B comes in, right? So you need to execute B because the new period for the B start, right? Therefore, the B has higher than A. B preempt, right? And then C comes in. Since C has a higher priority for this interval, so C preempt, then start A. So this is the way the RMS is working. And as you can tell, it only does preempt. There is no need to compute the deadline, like earliest deadline first algorithm. There is no such like recomputation of the priority. And that is one of the beauty of this RMS. And as you can tell, and the CPU utilization is not close to 100%, right? And that's the difference, or that may be considered as a downside compared to the earliest deadline first EDF scheduling algorithm. However, there is one of the most amazing discovery about this RMS. You should not forget this. This is truly amazing discovery in the scheduling research and scheduling study. So U is what? Utilization. What is how we can compute the utilization? That is the CPU burst over the period, right? And if you sum up all those CPU utilization for all the tasks, if this sum is less than n is number of tasks in the system times 2 to the power of 1 over n minus 1. If this inequality can be satisfied, then all the deadline of the periodic task for A, B, C can be guaranteed to meet. I don't know how this formula comes up, and this has been reported, and this has been proved, and this is one of the amazing discovery that has been found in computer science scheduling research. So for the same example, let's compute the CPU utilization, whether that inequality can be satisfied or not. So for the UA, utilization for A is what? So 42%, 25 over 60. And UB, utilization, is a CPU burst is a 15 time unit, period is a 40 time unit, therefore it's a 38%. And UC is a 17%. If I sum up, this is 97%. Now, let's compute the other right-hand side of the inequality. The formula was what? N over what? 2 times 1 over n minus 1, right? So n is what? 3, since we only have 3 tasks or 3 threads in our periodic scheduling problem. So 3 times 2, 1 over 3 minus 1, which is a 78%. Therefore, the right-hand side, the left-hand side is larger than the left-hand side. Therefore, the RMS cannot guarantee all the deadline of the task can be met. So as you can see, in this case, and when we vary a little bit of that arrival time of the task ABC, then you can clearly tell the A's deadline cannot be met. And remember, there's one important point that I would like to make. So when this inequality can be satisfied, if this is true, then we guarantee all the deadline of the thread can be satisfied for the RMS schedule, right? However, there's a very important point that I tried to make. If this is false, right? As in this example, then there is no guarantee. There exists a scheduling to satisfy to meet the deadline. There is no guarantee. Okay, and I would like to say there is some deadline can be missed, right? And I would like to say that way, but that's not the case, right? If this inequality is false, then there is no guarantee. There might, okay? Simply there is no guarantee to meet the real-time scheduling deadline. So I would like to re-emphasize this portion. If this inequality violate and there is no guarantee, I would like to re-emphasize this point. So let me show you another example. So this is another case, and in this case, the CPU burst of the B is a 10. So if you recompute this CPU utilization, sum of CPU utilization is 84% and 78%, which is clearly violate the RMS guarantee condition, right? So that means this condition fails. Again, that does not mean that there is no case for the deadline can be met for thread ABC. And as you can see, all the deadline is met, right? So this is what? The conservative assertion, right? Not the necessary assertion. So in spite of this condition violate, there might exist some scheduling to satisfy all the deadline of ABC. So that is the RMS scheduling. So let me re-summarize this RMS. And RMS is such an amazing algorithm. The reason is RMS is so simple and efficient. And once the static priority is computed, And this is a static. That means once it is computed, you don't need to recompute again. And the computation of the priority is so simple too, because it is simply based on the rate, which is CPU burst over the period time unit. RLMS is optimal for the static priority algorithm. There is no static scheduling algorithm better than the RLMS. If RLMS cannot schedule, no other static priority can. And this is just amazing. And there is a very complex proof for this one. I cannot understand how the proof proceeds. However, this is known fact, and this is claimed to be proved. So again, RLMS is optimal for static priority scheduling. RLMS cannot schedule, then no other static priority can. And one of the downside is RLMS is limited, and in what it guarantees, the CPU utilization bounded by n times 2 1 over n minus 1, which is a little bit less than ln2. This is about 69% of the upper bound. And if this CPU utilization, you're happy with this level of CPU utilization, then all the deadline of the given task can be satisfied. And however, if some relation, this inequality cannot be met, then there is no guarantee the deadline of the task can be met. And also remember, RLMS is only limited to the periodic thread scheduling problem. So once you deal with a periodic thread scheduling problem, then RLMS is not suitable. So this is the recap and summary. However, and you shouldn't forget this, how the RLMS scheduling is working and what is the task condition, whether all the deadline can be met for the given task under the RLMS. You must remember this scheduling algorithm. So this is the end of my lecture on scheduling. This is a summary. I go over the basic scheduling algorithm, and I show the shortest first and shortest remaining next time scheduling is the best. Unfortunately, this cannot be used in the real workload, and because it can lead it to the starvation. And also, I covered the multiple CPU cores scheduling algorithm. And so we talked about the shared queue and global queue and peer approach and core schedule related threads. And finally, I covered the real-time scheduling algorithm. In particular, I introduced two outstanding real-time scheduling algorithms, which is always deadline first and rate monotonic scheduling. And all these are such an amazing research topic if you're planning to do the scheduling research in the real-time setting or general purpose computing setting. And this is the end of the lecture for the chapter 6.